Thank you for having me. Abdul Karim Thiam, a PhD candidate at Lagos Laboratory. It is a laboratory aims for geophysical and spatial oceanography. So my topic of work is about mesoscale dynamics and its interaction with coastal upwelling in the northern Gulf of Guinea. So the Gulf of Guinea is a region in the eastern part of the tropical Atlantic Ocean. So it is characterized by a high coastal population density with activity like fishing and farming. Also, meanwhile, the regional climate is tightly condition of the ocean. So by the condition of the sun, we have a seasonal setting of upwelling, the equatorial one that you can see here, and the coastal one. So the appearance of these two patterns lead to a temperature gradient, a surface temperature gradient that enhance the so-called so that bring water vapor in the continent. And then this wind will meet the northeasterly wind that I do not represent here. And when they meet, they trigger some convective activity that is very important to trigger precipitation. And the maximum precipitation is located alongside this intertropical convergence zone. That is very important for the activities that I mentioned earlier, like farming and fishing also. So knowing the condition of the ocean is very important for this region and process leading to the setting of this pattern. Among these processes, we can have a mesoscale processes. And when I talk about mesoscale, I'm referring to equatorial and coastal tropic wave, and also process from mesoscale eddies. And we are going to focus on this last one. So eddies are quasi-circular structure that has the ability to trap water masses and travel to a long distance from away from the bone. So they have a spatial scale ranging from 10 to 100 kilometers and a temporal scale from day to a few months. So here, my purpose is to feature or to characterize the mesoscale eddies and try to find out how they can interact with the northern Gulf of Guinea upwelling system that you can see here. So to do that, I'm dealing with Eulerian simulation from NEMO models. It is a eddy resolving configuration, so that I use in the Gulf of Guinea with a resolution of 3 kilometers and 50 vertical levels. I use lateral boundary forcing from an initial condition from a Mercator analysis Gloris. And for the continental freshwater runoff is from East Basset Trip and IBAM Institute data from Congo River, for Congo River. And the vertical mixing was computed using a generic length scale formulations. And I have run the model for 11 years, from 2007 to 2017, with a 2 year of syrup and in a daily output. I have also deal with observation data like altimetry from SEMEMS and other satellite in situ and satellite data, blended in situ and satellite data like OESST, SST from MU, MODIS, and so on. I have also used PIRASHA data and data from thermosalinograph that was equipped in a commercial ship. I have also I have also perform the index section using the algorithm designed by Chignon and all that I apply on both the CMMs and Nemo absolute dynamic topography. So with this algorithm, the vortex or the eddies is identified by identifying first the local extremum, like a minimum or maximum absolute dynamic topography. And the edge is defined like the outmost close contour that contain these extremum local. And in addition of that, we can also record the radius of the eddies, the amplitude, the lifetime, and their trajectory also. And I have also perform a Lagrangian simulation to track water masses trapped within the eddy to know where they come from and what will be their fate. So I validate my model using against the observation data. So here it is for the model, and the other one is for observation. So SMAP should be here. I don't. Observation is here. Here is OUSST that I compare with the models, and I have also do validation with the C-surface salinity by comparing the track of pirata campaign and a commercial ship, and the absolute dynamic topography from models that I compare to the one for CMMs, and also the current from models that I compare with current from drift. This should be here. So we can see the upwelling well represented by the model where we compare it with OESST data. And also the Guinean current, like you can see here, is well represented from the model. So here I summarize all the all the comparison or validation that I made with other observation data that you can see here in terms of correlation, standard deviation, and root mean square error. So in a word, one bias ranging from 0.03 degrees Celsius to 0.63 can be found, and have a Frisch base from my model ranging from minus 0.52 to minus 0.15, and a weak absolute dynamic bias, it's nearly zero. So it makes us confident that our model is representing the main feature in this region, so we can use it for analyzing the mesoscale dynamics. So move on. Here I perform the extraction by comparing the extraction from NEMO and the one from altimetry from SEMEMS. So I represent here the eddy center, donc dot for cyclonic eddy and star for anticyclonic eddy. The first day they are detected. So the shaded pixel is the one that hosts at least eddy for a month. So it's on when we compare it, we find a very good consistency between the two products, Nemo and Samem saturation. And the associate radius of all this AD, we can see it. We have a very nice comparable values that you can find also. And for amplitude also, it's very similar compared to the altimeter. But we find more cyclonic eddies for Nemo, especially near the coast compared to altimeter. And also for the anticyclonic eddy, we have a comparable values. We have a 35 for Nemo and 34 for altimetric. So it's very nice, and it represents well the different patterns that we expect. So what I use, so to see the interannual variability and the seasonal of the detected eddies, I perform this by separating the detected eddy in different boxes, box 1 and 2 and box 3 at the vicinity of the Niger River. So we can see at every year, at least we found one cyclonic eddy. When we take the box 1, we have 10 years of out 11 that we can see the detected cyclone, and the same one for box 2 and box 3. And when we analyze closely the seasonal variability, we find seasonal modulations. We find a peak of cyclonic eddy during the minor upwelling season and a max during the major upwelling season. You can see it for the box 2 also, but it is less evidence with the box 3. So to try to explain the mechanism behind the generation of the eddies in terms of baroclinic to try to explain it. So the question is based of the gradient of the potential vorticity. So for an eddy to be barotrophically generated, the value of C should be changing C. The sign of the C value of the crystal should change, and we should have also weak valence for eddy to be barotropically generated. So what we find here, I share the parameter C here, and I add the eddies detected at the first time we see them. So for the July, August, September, and for the bottom one we have the July situations, and I add this eddy center and the contour here that you can see, cyclonic for the blue edge and anticyclonic for the black ads. So I summarize it here by putting different class ranging from -25 to 25, and I add the number of edit belonging to each classes. So we can see a very consistency between the two product altimetry from Siemens and Zinemo. So most of the cyclonic and anticyclonic eddies from the altimetry are barotropically generated, but there are differences when we compare from NEMO, particularly for the cyclonic eddies. There is a deviation from the low values here. So that means other process like baroclinic should be invoked for cyclonic eddies. So after that, I do a case study to try to see how eddies can interact with the coastal upwelling and modulate it. So here is a case study of July 2016, where I focus on the cyclonic eddies found here. And we can see this signature in salinity here, and temperature that we will quantify later. And the associated signal of absolute dynamic topography is a minimum here that we can see. In terms of relative vorticity, it is a positive relative vorticity. And when we plot the cross section here, we see that the core of the eddy is found around 20 meters here. So to know where the eddy, the water mass is trapped within the eddy come from, I perform a Lagrangian simulation. So I put more than 1,000 virtual particles here at the date the eddy was firstly detected. So I track back this particle to see where they come from. So before the eddies formed, they were at the east and the west side of the Cap 3 points at a depth ranging from 15 to 30 meters, and the associated temperature is they was cold before warming within the eddy, and salinity associated is they was very salty, and once in the eddy they are refreshed. So here I try to find the close relation between how the eddy displacement and the eddy center and upwelling threshold displacement, how they interact, how eddy can modulate the extension of the upwelling, here defined by the isotherm of 25 degree that we can see here. So combining the two frame, we see that there is a close relation between the displacement of the eddy center and the upwelling threshold. They are correlated to coefficient of correlation of 0.64 and in a level of significance of 99%. So here I quantify this relation in terms of heat budget. So the temperature within the box depend on the term like advection, lateral diffusion, vertical diffusion, and the interaction of the ocean atmosphere that you can see here. But what I do, I isolate the contribution of the eddy from the mean situation or the mean state by doing a filtering by using a cut frequency of 1/30 days, because the eddy lasts at least a month. That's why I use these frequencies. So, and at this cutting of frequencies, the dominant term is the advection term. That's why I only shade it here that we can see. So we distinguish two phases. The first phase is since the eddy is born to to 26th of July, we have a cooling of the temperature, and in a second phase where the eddy warms the upwelling cells. So in terms of advection, how I explain it, so it is highly the eddy cold temperature, so that you can see here by the dash line. It dominates by eddy, and at the second, it's for the warm that we see here. And when we take at different boundary of the box, we see that eddies cool the upwelling by the eastern side that you can see here and the west side, and they warm it from the east side mainly. And for the south, we have a cooling at the first phase of cooling phase, and at the second phase, they warm it by the south far. Just to try to see in a 2D situation, we have the Ghanaian current that flowing here and bring warm water in the upwelling cell that you can see here. Meanwhile, the eddy is cooling it, like here, that we can see in blue. And when eddies enter in the box, they are evacuated by the Guinean current, like we can see here in this color. Meanwhile, the eddy is warming the upwelling by advecting in from warm water in the upwelling cells. And for the south boundary, we see that the detachment of the Guinean current here called the south boundary that we can see here. And when he flow back to the coast, it warm it again. And when we take the contribution of the eddies, we see globally we have similar pattern, but globally he is a cooling phase. So in conclusion, cyclonic eddy preferentially form in the upwelling east in the upwelling area eastward of Cap 3 Point and Cap Palmas. And cyclonic eddy are mostly found offshore along the Guinean current latitude and east of 3 degrees at the vicinity of the Niger River plume. 38 cyclonic and 35 anticyclonic eddy trajectory were detected over the July, August, September period from the NEMO, and 22 cyclonic and 35 anticyclonic eddy trajectory from the same altimetry. Our NEMO simulation and altimetry from SEMEMS agree that cyclonic eddy generation could be mainly explained by barotropic instability, whereas baroclinic ones should be involved for cyclonic eddies as found in NEMO. In our case study, eddy influence coastal upwelling at intraseasonal scale in two ways. The first one is upwelling enhancement and an offshore advection of cold water in the first phase from July 17 to July 26. And at the second ways, it prevents from upwelling establishment in a second and longer phase by advecting warm inflow water through south and mainly eastern boundary from July 27 to August 13th. So one thing I will add before, after is I'm open to work for any related topic. So feel free to reach me out via my email address. So thank you for your listening.
Thank you very much, Karim, for your nice presentations. Obviously, we'll put the PDF available for everyone to have a look at and contact you if they want.
Yeah.
So for now, we don't have any question. So can wait a few seconds to see, but yeah, you have greetings and kudos from people in the chat also, so well done. Just looking if I have question coming. No, okay, so I don't think we have any question coming for your presentation. Oh, okay, so no, we have one. We have one, sorry. Okay, yeah, so I'm missing the first part of the question. So, well, the question are in the wrong order, but So Indian Ocean, especially in South Africa, are experiencing a lot of aftermath of cyclones and hurricanes, such as floods, which destroys infrastructures and affect the ocean ecosystem. How can this research help?
Which destroy infection and affect the ocean ecosystem. How? I don't understand what he really mean. Which destroy infection and affect the ocean ecosystem.
I think it's like how your research can help prevent like the destruction of infrastructure.
Infrastructure, yeah, but here I deal with ocean eddies. According to my extraction that I made, maybe the eddy doesn't hit the coast. They expand offshore. It's not atmospheric cyclonic eddies that can travel all the continent. It is located in the, what I can say, in the middle of the ocean. But yes, for ecosystem, maybe it can enhance maybe for the chlorophyll bloom because eddies can like for cyclone can boost the generation of chlorophyll by advecting rich nutrient water upward. Yeah.
Thanks a lot. So we have next question. What was the essence of using the Lagrangian principle in your study?
Yeah, to track particles. So, do you know when we want to flow the eddy, we need to track the particles to know where they come from and what will be their fate. From that, we can see the different property associated to the eddy. And also, when we are doing a potential vorticity analysis, it is preferential to use a Lagrangian simulation since the potential vorticity is conserved for each particle. So you can see how the eddy was generated. It's very essential to use Lagrangian simulation.
Thanks a lot. And one more question. Are the edges strong or powerful in West Africa, especially in the...
Yeah, they are also strong because we can see eddies, the range of the eddies range more than 100 kilometers, and they travel a long distance, and so it's very powerful also in West Africa. Yeah, but for what I can say, it's more like when we go at the north side that it is very frequent there compared to the Gulf of Guinea.
Thanks a lot. And I think we have time for one more question. Is coastal erosion caused by eddy in coastal Africa?
No, I don't think so. I don't know, so, because yes, if it is close to the coast, but it's not tightly related. Yeah, for sure.
So, we have few more questions. We will have time to do one or two more. What software did you use to refine your results?
What she mean from the what software do you
I
use to
think, did you
define?
use Python or
Yeah,
MATLAB?
yeah. Okay, I use Python. I deal with Python, but for the eddy extraction, the code it is implemented on MATLAB.
Okay, okay, good
But
to know.
most of the result is made by Python, the plotting, yeah, and the analysis also. It's just the
Okay,
eddy extraction that I use a Python script, MATLAB script.
okay, okay, thanks a lot.
Yeah.
And yeah, so we will do two more questions and then we will have to stop. Was there any sea surface temperature contribution to the study on edges?
Was there any sea surface temperature contribution to the study on eddy? I don't know. I don't understand also what he mean from
Just,
there.
yeah, I think did you study the SST when you
Yeah,
studied
yeah,
this?
I show it on my presentation, so maybe it was not clear from at this point. I use sea surface temperature to see to look at the signal associated to the eddies, and also a heat budget in the mixed within the mixed layer to see how temperature trends can be triggered by by the eddy setting.
Okay, okay, thanks for the explanation. And one last question. What are the key impacts of mesoscale processes in the northern Gulf of Guinea on marine life and coastal communities' activities across season? So it's
Okay.
general question.
Yeah. For the impact, mesoscale eddies can enhance the upwelling, like I show by offshore advection of the upwelling. So where we are, water masses that is offshore advected, they should be replaced by, according to the equation of the conservation of masses, by upward water. So you enhance your upwelling from there. And the rich nutrient water upward at the surface is very rich in nutrients, so it can help for the phytoplankton and zooplankton growing, and it's very favoring the fishing, as you can see. And the last one is coastal community activity. Yes, like fishing and also the climate. Because when we have upwelling, like I show, it enhances the wind towards the coast, and these winds are very rich in water vapors. And when they meet with the northeasterly wind, they can trigger convective activities that favor cloud and so precipitation. And it's very useful for the agriculture and farming or farming. Yeah.
Okay, thanks a lot for the explanation. That
Yeah.
was
Thank
the
you.
last question
Okay.
for you today.
Okay.
And yes, thanks again for your
Thank you for
presentation.
having me, everyone.